everyone, and welcome to episode 4 of Q for Problems. Today we'll be looking at problem 4 from the Project Euler problem set, and it wants us to find the largest palindrome made from the product of two 3-digit numbers. So here a palindromic number is a number that can be read the same both ways. So for example 9009 as is shown in the problem. So let's get into it. So we can start off by creating a list of all the 3-digit numbers. So that'll be 100 plus till 900. Space in there. So you can see this is a list of all the numbers from 100 to 999. The next is to do the outer product of all these numbers. So we can do that doing n times each right of n. You can see that produces a large matrix. So what's actually happening here is it's taking the value of 100 and multiplying it by every single number in this list, and that gets us our first row. It then gets 101 and multiplies that by everything in this list and gets the second row, and etc. for the rest of the list. And it produces this large matrix. So this can become a problem in terms of memory if you have a lot of numbers being done here, and we will see that does become a problem and how we can fix that. So the next thing to do is to raise and distinct this list. So raise to flatten it and then get just the unique values, because the comparison is probably where a lot of the performance comes in time wise. So we want the values, this list to be as small as we can before doing that comparison. So if we say P is distinct raise of M, and there you can see now we have a flat list of distinct values. So now what we need to do is identify which values are palindromes. So I'm going to create a function, palindromes. So this function is essentially a filter that will filter out any numbers that are not palindromes and only return those which are. So to create this function, I'll just start outside it and do string p. So if I convert everything to a string and reverse each item, all I need to do now is compare each of these items with the original p. So rather than do a string comparison, I'm going to cast back to a list of longs. You can see that leading zeros are actually dropped from this, but that's okay because any number that has the leading zeros isn't going to be a palindrome anyway. However, the comparison using longs rather than strings is for performance. Comparing strings, because each string has to actually compare its individual elements, whereas numbers can be compared a lot faster. So converting that back into a list of longs. So all we need to do now is do where p is equal to each of these reversed items. So this will return us a Boolean list where three values correspond to palindromic numbers. To get the indexes of those numbers, we use the where, and then we can index back into p to actually get the numbers themselves. And you can see these numbers are all palindromic. So this is going to be our palindromes function, essentially with the p's replaced with x's. So I now all that I need to do is to max on palindromes, and you can see that returns me the correct answer. So our S1, our solution 1, is going to be the max of palindromes on distinct raise n times each right of n assigned to 100 plus till 900. And if I do S1 with no arguments, you can see it returns me the answer. So we can actually generalize this solution a bit rather than just having it apply to the actual 3-digit numbers. We could do this for any number. However, to do this, we need to recreate this logic and be able to create a range of numbers. So to create a range, if I start with, say, a lower bound equals to 1, an upper bound equals to 9, and a step size of 2. Now our step size is always going to be in ones for this, however I just want this to be a general range function as well. We can actually get the number of values we need by doing 1 plus u minus l, so the upper range minus, or upper value minus the lower, divided by the step. That tells me how many values I'm going to need in that range. So if you think about this is the lower and upper in a step of 2, we're going to have 1, 3, 5, 7, 9. So we're going to have 5 values. So this tells me how many values are going to be needed. To get the unscaled range of values, I just do till. So these are the values, but they're unscaled at the minute to actually fit the range. So first of all, I need to scale by the step, which I always need to do. So I've scaled by the step here now. The final part will depend on the type of range that you want. So I'm going to create this function as range 0. This is going to be the base. It is going to take lower, upper, and step, and then it's going to take a scaling function. So the scaling function will then apply to what we just had. So if I define that, and then I can define a range function. So this will be just a range of step 1. So let's say if I say the range base function, and I have my lower is going to be x, my upper is going to be y, my step is always going to be 1 for this normal range function. And now if I do my lower plus, so the lower plus is a function, the scaling function, and it's going to add the lower bound to this. So if I run this now, range of say 1 to 9, and run that, you can see I get all the numbers from 1 to 9. If I change 1 to say 4, you can see it's only 4 to 9 now, and the ends are inclusive. So the reason we want this to be general and have this scaling function is because I can actually create a reverse range function in the exact same way, except I use a different scaling function. So if I paste this in, again, just the same as before, but instead of scaling it with the lower plus, I actually do the upper y plus and the neg apply. So what that does is it's going to do the negative of all these numbers. So remember, these numbers in the example I had before were 0, 2, 4, 6. So it's going to be the 0. Then it's going to plus the max of the range, the largest value in the range. So that would have been 9. So it'd actually be 9 minus 0 would be 9. 9 minus 2 would be 7. 9 minus 4 would be 5. 9 minus 6 would be 3. And then 9 minus 8 would be 1. So it's actually the reverse of this range. So if I run that, and then let's just grab what I had before. Let's do our range. You can see it actually gives me 9 backwards to 4. So that's why I've created this base range function. However, what we're going to be using anyway is this base range function in our actual solution. So our general function, S2, is going to be max palindromes, like we had before, and distinct rays, which is also what we had before. So to actually create this as a composition function, i.e. like a function, it's going to be a function without any brackets, because the actual argument is going to be the very last value. You can't have any assignments midway through. So instead of the assignment of the n, I'm going to actually do a lambda function here. And that's basically just still doing the outer product, but just using the lambda function instead. And then if I do range, and then I use the double colon here to create the composition. So if I run that, you can see composition. And if I do S2 on, let's do the 1-digit numbers. And you can see that gives me 9, because all 1-digit numbers are going to be palindromes. Let's do the 2-digit numbers, 9, 9. You can see that gives me, this is what was actually shown in the question. If I do the 3-digit numbers, this should be the same solution as we had before. And if I do the 4-digit numbers, let me see. So this is actually going to take a few seconds to run, because it still has to create the large matrix with the outer product. However, you can see I do get the answer. Now, if I want to do the 5-digit numbers, the 5-digit numbers will actually use ups of 16 gigs of memory. So I can't actually do it here in my free version of KDB. However, that is a problem. They use so much memory, and then if I want to do the 6 or 7-digit numbers, it would use even more memory. So we can instead devise an iterative approach, which is going to be a bit slower because it's not using it's not pre-creating the whole matrix and then doing the operation on it. It's actually going to do them one by one, which in general is slower. However, it means that I'm not having to store this large matrix all at once. I'm going to have to store each row of this matrix essentially one by one. If I start off with x equals 100 and y equals 999, and then our r is equal to our range between these, just as we had before. So if I start off with that, what we're going to be doing is doing palindromes on r times r0. So it should be times. So essentially, R0 is 100 and R is the full list of numbers. I'm just doing the product of those. So I'm only doing each of the products one at a time rather than doing them all at once using the outer product. So if I do palindromes that, it will return me all the list of palindromes from that. If I then do the next one, you can see I get all the palindromes from that, and so on and so on. So to make this general, I can do surround this with brackets to create this this composition, and then I essentially can do this on each of R, where R is going to be this range. So you can see this gives me a large list of all the palindromes, and then I can raise this list to get it flat and then just find the max value. And you can see that this agrees with the answer we had before. So just to create this into a function, so S3 is equal to, or sorry, assigned to the function range. Yep, so this is in the functional form. So I can actually do S3 on our original numbers. Sorry, it should be another 9 there, and there you can see. No, the only problem with this is it is actually still quite slow. So if I wanted to do the 5-digit numbers, it would actually on my computer take 14 minutes. So to fix this, instead of having each here, the alternative is to use parallel processing and replace the each with a peach. So what that will do is, rather than doing, it will essentially look at this range. It has all the numbers 199. So if I started with 8 secondary KDB processes, each process would get 1/8 of that. So it would be divided up amongst them, and each of them would share essentially the calculation. And then once each of them is done, they return to the main thread, and it combines the results and returns. So the result will look exactly the same as just using each, but it will be a lot more performant because the work is divided up amongst the secondary processes. And if you don't start the KDB with secondary processes, this just behaves the same as each, so it will still work. So we'll have a look at the performance benefits of doing that in the next section. So looking at performance, this function perf compare creates a comparison of the 3 functions with many different arguments. So essentially, we run it with for 1-digit numbers, for 2-digit numbers, for the 3-digit numbers, and the 4. And then also we just do the normal performance test on S3 with the 5-digit numbers and S4 with the 5-digit numbers to compare the parallel computing, the use of Peach. So these did take quite a long time to run, so I did pre-do it. So we're just going to actually look at the results here. So the compare returns a dictionary. If I look at T, it returns a dictionary with the normal comparison of each function, or the normal values of each run. But it also then has the best time, the ones that had the best time, the functions had the worst time, the best memory and the worst memory. So just having a look at those. For so the comparison, you can see the CMP column. This is for the 1-digit numbers, 2-digit numbers, 3-digit numbers, and 4-digit numbers. So S2 was the best for the one digit numbers, because obviously when we're using Peach for S4, the cost of actually having to break the problem into the eight threads and send it to the eight threads has to be serialized, deserialized, and they have to compute and then send it back. That's obviously just not worth um, doing. However, as we can see for all the other digits, the use of the parallel algorithm was actually the best um, in terms of time. So for you can see here just to get a clarification of the best, or sorry, the biggest digits. It took about almost 1.5 seconds on average per run. So if we look at the worst time now, you can see that S4 was, again, because I mentioned there the parallelism wasn't worth it, was the worst. But in all cases, then S3 was the worst. However, S3, the only benefit is that it can handle it doesn't have a high memory usage for if we went to 5 digits, which we'll see in a minute. So if I look at the best mem, and I'll just put the worst mem up as well. So these two tables are the best and worst mem. You can see that S4 was the best in all cases. However, that is because a lot of the memory intensive stuff is done on the secondary threads, which isn't shown here. This is only the memory usage on the main thread. And the worst mem then was S2, of course, because it has to generate that large matrix every single time. It would still be much worse than S4, even if that included all the secondary process memories as well. Uh, So just looking at a comparison of the parallel with the non-parallel, the use of peach instead of each. So T1 was for S3, and as you can see here, it took 23 minutes. So whenever I first did this, it took 14 minutes. This time it took 23 because it depends on the operating system, things like that. However, all that's relevant is that it did take a very large amount of time to do for 5 digit numbers. And if I look at T2, which was for S4, you can see it took about 4 minutes. So it was a large factor greater in terms of performance, but it still takes quite a long time. That is with 8 secondary processes. So yeah, that is the performance comparison. Please post your solutions, comments below, and yeah, thanks for watching.